Hello, this lecture is on applications of refraction. So you learned what refraction was, and this one is going to talk about why we care, what real-world applications there are, and maybe times in your life that you've observed something that was due to refraction that you didn't even know. So if you've ever wondered things like, why does it look like a straw is broken when it look at it from the side of a glass, or what's happening in those amazing cool fiber optic cables, or really what makes a rainbow, this is the lecture that's going to finally answer some of those questions for you. So that funny picture of the broken looking straw from the last slide was an example of an image made with refracted light. And actually, anytime you look at anything through a surface, through a window or through water, you're not actually seeing the object where it exists. You're seeing where the light looks like it came from. You're seeing an image of that object, but that light actually didn't come from that spot because the light is being bent as it crosses all of those boundaries. So for example, if we had a fish underwater and we wanted to know where would the image of that fish appear to a person out of the water that might be interested in hunting that fish, we would start with the understanding that the fish is reflecting light in all directions. It's not making its own light, but it's reflecting the light in all directions. The person outside of the water needs some of that light to get transmitted into the air. So if we pick a couple light rays that are going to go through that boundary and out into the air, we can use ray tracing to figure out where would the person looking at that fish think the fish actually was. It doesn't matter which two light rays you choose, but you do need to remember the rules of refraction, which are when light is hitting a less dense medium, it's going from a slower medium into a faster medium, from water into air, it's going to be bending away from the normal line. So I went ahead and took two light rays and bent them away from the normal line. You could calculate all these angles if you wanted, but this is just kind of a sketch. So now if you imagine those are the two light rays that the person trying to hunt the fish sees, that person thinks those light rays came on a straight line, and so it traces them back using some virtual light rays, and where those light rays appear to have intersected, that's where we think the fish is actually located. So our brain actually places the image of the fish closer to the surface of the water than the object, which is part of the reason it's really hard to catch fish. That image is virtual because those light rays didn't actually come from that location, right? They just look like they did. And it's also an upright image because the fish is still top fin up. So the second important phenomenon I want to talk about is something known as total internal reflection. So this occurs when you have light that is starting in a slow medium, like the water example that we just used before, and it's trying to get into a faster medium. Now, if we shoot that light ray straight up, like in this first example, we know it transmits easily straight into the new medium. It's going to speed up, but it doesn't bend. However, when you start changing the angle and you start sending that light into the new medium at an angle, right, it follows Snell's law. So we start bending away from the normal. And the steeper that angle of incidence, the more it bends. And the steeper, the more it bends. And if you think about it, we're about to have a problem here because eventually that angle of refraction is 90 degrees and it's bending so that the refracted light is actually going right along the interface between those two surfaces. That magic angle is known as theta c, or the critical angle of the light. And so it's a critical angle between, say, for example, in this example, water and air. And it's an angle you can calculate, and it's really important in physics because if you try to send light in at any steeper angle than that theta c, none of that light is actually transmitted. It actually all gets reflected instead back into the same material, and that is known as total internal reflection. So this phenomenon only happens when we're going from slow to fast, and the Snell's law works with this. You can calculate theta c if you use 90 degrees as your theta r, or your refraction angle. And so this tells you basically the angle beyond which no light will actually be escaping the material and all of the light will be reflected inside the material. Why do we care about this? Let's talk about it on the next slide. So we've used this property of total internal reflection to make one of the most critical pieces of technology that we use for information transfer these in our current era, known as fiber optics. Fiber optics sometimes are called light pipes because they are basically a pipe for keeping light in. If you have a fiber optic cable, what you basically have is an inner core that's got a really high index of refraction. So that's like the really, really slow material, right? Although remember that light still goes really darn fast. And then we have an outer cladding or a casing that has a really, really low refractive index. So light would go really fast through it. So what happens then is when you send the light in, when it hits that boundary, instead of transmitting into the new material, we actually reflect, and we can reflect even as this pipe changes orientations and is bent to keep the light in this material. So normally light goes in a straight line, but fiber optic cables allow us to bend the path of the light through this process of total internal reflection. We can force that light to stay inside the pipe and go in curved paths. This is a picture of an actual material exhibiting total internal reflection. If we were in class, I'd show you a demonstration of this, but I don't have it. It's not in my classroom right now. But it's pretty cool to actually see that light reflecting off and bouncing and going around the pipe. But you know, in the world, the reason we care about this is because light goes super fast, but it goes in a straight line. So when we're trying to communicate using light from one side of the Earth to the other, we've got two choices. We either beam it up to a satellite and back down, bounce it off a couple satellites to get over to China or India or something other side of the Earth, or we use a light pipe or a fiber optic cable that can allow the light to go in a curved path around the Earth and get back to the other side of the planet. And so that's why we have these massive fiber optic cables buried under the ocean floor to allow us to communicate with light in a curved path. Also, apparently you can get a hoodie for like $200 that has amazing fiber optics in it. So if you're looking for a good holiday gift idea, that might be a good one for you. Quick little sample critical angle calculation. What is the critical angle for a diamond in air? So remember that diamond is the slowest material. So this would really make a good fiber optic cable if it wasn't so expensive and brittle. So if I was solving this, I would know that light would have to be starting in the slower medium. So the diamond would have to be my N1. And I know that N for diamond is 2.4, and the air would be the fast medium, so that's my N2, which is 1.0 for the index of refraction. And if we're talking about critical angle, that means that theta 2 is going to be 90 degrees. That's the angle along which it stays into the original incident material. So I use my Snell's law, and I just plug in 2.4 times sine of theta c equals 1.0 times the sine of 90, and you calculate theta c, a critical angle is 25 degrees. So what that means is for diamond, if we're entering any bigger than 25 degrees, it actually stays inside the diamond. This is actually the reason why diamonds are so sparkly and used in fancy jewelry, is this idea of critical angle. So when a diamond carver cuts a diamond, they cut it in this normal proportions so that light coming in the surface, at the top surface, this is not, we're not going to have a critical angle situation because we're going from fast to slow. But once we're in the diamond, this back surface is designed so that the light hitting this will be hitting it at more than 25 degrees, and it will stay inside the diamond. And then that light hits this other surface, again at more than 25 degrees, so it stays inside the diamond. And then it hits the top surface, and that's when it finally is less than 25 degrees and it's able to get back out again. But the reason that this is useful is because it means all the sparkly light shines back out the front face of the diamond, and it makes it look super sparkly. If you carve the diamond wrong, too deep, then the light's going to escape out the back. That doesn't look sparkly. Or if you make it too shallow, then the light escapes out the side of the diamond, and it's not sparkly either. So there's a real art in carving diamonds so that they're super sparkly, and they make light reflect back out the front surface. The third interesting property of refraction that I wanted to talk about is the fact that the index of refraction depends on the frequency of light. This is a little bit surprising. Refraction itself is actually a function of resonance. If you learned about that in the future in an earlier physics class, it was kind of an advanced topic that was like optional extension for some people. But resonance is the idea that materials vibrate with certain frequencies. So in general, the reason the bend is happening has to do with the vibration of the material that it's hitting. And that means that it can depend on the frequency of the light that's coming in. And so functionally, this means that different frequencies of light or different colors have different indices of refraction. That means they go at different speeds in media. They all go the same speed in vacuum, but once you start going into glass or plastic or other things, different colors of light are going to go at different velocities. The rule of thumb is that the higher the frequency of light, the slower it goes. So that means the purpler it is, the slower, and the more it is bending at the interface. So red does not bend as much as purple bends. So a prism is an optical device that uses this idea that the frequency of the light dictates the speed or the amount of refraction to actually do some really interesting things with light. This was the first, Isaac Newton was the person that first discovered that white light was actually made up of other frequencies through use of a prism to separate or scatter light in different colors in different directions. So if you start off, a prism is usually thought of as a triangular piece of glass. And if you think about the light ray coming in, like a red light ray hitting the side of that prism, that light ray is going to bend towards the normal line. Don't forget to draw your normal line kind of at an angle there because the surface of the prism is an angle. And so it slows down when it hits the glass. And then that light ray is going to go through the prism and hit the back surface. And now it's going to bend away from the normal line, which is still sort of downwards. It's, based on the orientation of the prism and the orientation of those normal lines, that tends to bend the light twice sort of downwards, away from normal. Now, if you picked a different color light, like green, it's going to do the same general bends. However, its bends are a little bit more dramatic because it is a higher frequency of light. And purple light is going to bend even more dramatically. So we had this white light coming in, all the colors coming in, and by the time we have passed through the prism, those lights have spread out into different colors. This is called dispersion or separation into colors. So this is kind of a drawing of a prism doing this with real white light, and I'm sure you guys have seen before rainbows being created when white light passed through kind of glass or prism shaped objects. But maybe one thing you didn't think about is that shape of that prism, that triangle, is very similar to another shape of a raindrop. And so it's the same phenomenon. It's the idea of light bending different amounts based on its color that is going to be the physics behind why raindrops make rainbows. Rainbows, it turns out, are a tidbit more complicated than prisms. They actually use reflection in addition to refraction, so we're actually talking about the second order reflection, but it is a similar idea. You can see when that sunlight hits the top surface of that raindrop, the white light comes in together and it starts spreading out, and every time we go through a surface, we're going to spread out more. This picture is actually really neat because it kind of explains why when we look at a rainbow, we see the red light on the outside, on the top, based on which drops are sending the red light into your eye, and then the purple light appears to be on the bottom because it's the drops that are lower that have that steeper bend that is sending the purple light into your eye. And there's just a picture of rainbows because you can never have too many rainbows in your life. Oh, this is a double rainbow. So interesting physics behind the first rainbow, the bottom one, we see that typical red on the top and purple on the bottom. The double rainbow is actually made by a whole nother cycle of reflections inside the raindrop, and you end up inverting or getting different colors on the top and the bottom. So if you have the luck to see a double rainbow, notice in particular how the colors are flipped in that second rainbow. Okay, so let's just take a quick second, revisit that essential question. Why do we care about refraction? What are some real-world applications and things that you've noticed in your life that maybe owe their explanations to refraction? Thanks for watching.